Hello everyone, I'm Zhai from Rutgers. I'm going to present our paper C2S, Translating Natural Language Comments to Formal Program Specifications. This is a joint work with the researchers from Purdue University and Nanjing University. Formal program specifications are essential for various software engineering tasks, such as program verification and software testing. However, manually composing formal specifications is time-consuming, error-prone, and requires substantial expertise. This motivates us to provide automation support in program specification generation. So, where do we infer specifications from? Before answering this question, let me ask another one. How do we know the semantics of a method? Normally, we read the natural language comments, which informally describe the semantics. For example, this table here shows the comments of the method remove first of the class linked list. The first sentence is a complete description of the functionality. The third part describes that a certain condition triggers a particular type of exception. The returns part describes the return value of this method. So now the question is that, can we translate the informal comments into formal specifications? The answer is yes. This is the direction we try to explore in our paper. There are existing techniques that generate specifications from code comments. However, the existing approaches all rely on patterns that are summarized manually. These patterns have some drawbacks. Firstly, they require substantial manual efforts and can only work for very limited comments. In addition, the patterns are context unaware. For example, these two methods both have the comment return the first component. The one at the top method means that the first component in the receiver object before or after executing the method, since this method execution doesn't change the receiver object. However, the one at the bottom method means the first component in the receiver object before executing the method, since the method execution removes the first element in the receiver object. From it, we can clearly see that a comment can be interpreted differently in different contexts, but a pattern can hardly capture the differences. So our goal is to devise a general approach which can address these limitations. In order to compose specifications, a lot of work has been devoted to design formal languages. Java modeling language is one of them, and it has been widely used by developers to provide specifications for JDK library methods. JML uses annotations to distinguish between different kinds of behaviors and different specification types. Here is a typical example. The part under the tag exceptional behavior describes the exceptional behaviors of this method. The formula that follows the request tag is the exception trigger condition, and the one after signals only is the corresponding exception type. The part under the tag normal behavior describes the normal behaviors of this method. The formula after ensures describes the execution effect of this method. Our basic idea is to treat natural language comments and JML specifications as two different languages expressing the same semantics, and formulate the specification translation task as a syntax-guided synthesis problem by assembling primitive tokens. The two tables here separately show the comments and the specifications of the method remove. Based on the annotations, we can associate a natural language comment and a JML specification. In this way, we can obtain alignments between natural language comments and JML specifications. Then we can use the tokens that are associated with the words of a comment to synthesize specifications for a target method. Here, the reason that we resort to search-based technique rather than machine learning techniques is that the number of available GML specifications is very limited, which may lead to the overfitting problem. Here is our design. It consists of two phases. The left one is the search space preparation phase, and the right one is the specification synthesis phase. The inputs of the left phase are natural language comments collected from Java documentation and corresponding GML specifications from the GML website. We begin by using the association engine to automatically couple each specification with a natural language comment, and the generated comment specification pairs are fed into the tokenizer to build word token pairs, which will be used to synthesize specifications in the second phase. The inputs of the second phase are a given method with natural language comments and the word token pairs. Then we will extract all tokens that are associated with the natural language words in the given comment and generate specification candidates by assembling tokens based on syntax rules and the context of the target method. The first component is the association engine. It automatically couples the specifications with corresponding comments based on annotations to prepare comment specification pairs. Then we will use the preprocessor to remove unnecessary information and normalize the text to get more general comments. It mainly performs three tasks. The first one is to remove the stop words. The second one is to reduce derived words to their word stem. For example, the word insert here is transformed into insert. The last one is to lowercase all the words. After the cleaning, each comment is split into individual words by space. Next, we will use IR Translator to generalize a GML specification in the text form to an abstract IR form, which is represented using AST. It works by substituting the concrete parameter names with placeholders in the form of pi and t, which means the ith parameter with data type t. There are two main reasons for the generalization. The first one is to facilitate the instantiation of the synthesis results with concrete information belonging to the target method. For example, assume the parameter name element is not generalized and hence becomes part of the token set that would be used to synthesize a specification. It's very likely that a target method with similar specifications does not have a parameter with the name element. Then it would be very difficult to replace it with some other parameter name, as we don't know what the element represents. By contrast, with the placeholder p1 and t, we know that it's the first parameter with the data type t, and thus finding a replacement is much easier. The other benefit is to reduce the search space by decreasing the number of tokens used to construct specifications, since parameter names can be diverse. After we have the pairs of preprocessed comments and generalized specifications, we will use the tokenizer comment here to construct pairs of NL words and AST tokens. We can see from the table that each natural language word is associated with some tokens, which will be used to synthesize specifications. Now we have pairs of natural language words and specification tokens. We are ready to generate specifications. Given a method with comments, we will first extract all tokens that are associated with the natural language words in the given comment, and then we will generate candidates by assembling tokens based on syntax rules and the context of the target method. I will use an example to show this process. Initially, we have these tokens. Here, \result is a keyword used to represent the return value of a method. Contents here is a pure method used to encapsulate some primitive action, which is called method placeholder in our system. P1 at object is one parameter placeholder. Note that other placeholders like P1 at int may also be associated with one of the natural language words, but they are not included in the token set, because the first parameter of the target method is object rather than some other data types like int. Then in the first iteration, we can construct these two incomplete ASTs based on specification syntax. Note that the reason that \result and -1 can be assembled together is that the return type of the target method is int. Then in the second iteration, the ASTs 3 and 4 are constructed. After that, the third iteration will produce AST5 and 6. Finally, the whole tree is created in the fourth iteration. After the whole process, we have created 4 complete logical specification candidates, namely 3, 4, 6, and the whole tree. IR candidates generated in the previous slide contain parameter placeholders and method placeholders, so they need to be separately instantiated with formal parameters of the target method and concrete Java method in the class or superclass that contains the target method. Take this method here as an example. The IR this dot contains P1 and E is generated. Here we have the method placeholder contains and the parameter placeholder P1 and E. P1 and E here means the first parameter with the generic data type, which can be matched to the solo parameter V of the target method at the vertex. So we just substitute P1 and E with V here. The method placeholder contains takes the generic data type as input, so any method in the target class that doesn't have parameters and any method whose first parameter data type is not generic are precluded. Then we compare the word vector of the abstract method name contains with the word vector of each concrete method name, and the one that has the highest similarity is the method contains vertex. So we substitute the method placeholder contains with the concrete method name contains vertex to get the final specification. This dot contains vertex V here. Lastly, we use the specification checker component to eliminate invalid specification candidates. It works by transforming the specification candidates into test oracles and then adding these oracles to existing project test cases written by developers. Here, we trust these project test cases as they were the ones used in unit testing and regression testing. Any specification candidate that triggers violations in these test cases are deemed as invalid. I will show this process using an example. This statement here is from a test case written by developers, and our system generates this specification for the method remove. Here, \old means the value of its parameter before executing the method remove. We first instantiate the specification by substituting general information with concrete information. For this case, we will substitute the formal parameter index with the actual parameter 2. Then we substitute the keyword \result with the variable name ret. Also, we substitute the keyword \old with the cloned receiver. After this instantiation, we can get the specification showing here. Then we instrument the assertions and the related code into the existing test cases. After that, we can run the instrumented test cases to help eliminate incorrect specifications. Now is the evaluation part. We evaluate our approach on 5 projects, and the table summarizes our results. In total, we can generate 1,145 specifications for 511 methods of 64 classes. This table also shows that our system is cross-project, since the search space of IR tokens are extracted only from the project JDK, but we are able to generate specifications for other projects. To measure the effectiveness of generating specifications, we manually check the precision and the recall. We say that a specification is correct when it's consistent with the source code. We define precision as the ratio between the number of correct specifications and the number of generated specifications, and we define recall as the ratio between the number of correct specifications to the total number of correct specifications that are supposed to be generated. We compare our system with 3 state-of-the-art approaches. Among them, add T comment does not handle normal post conditions. Pterodactyl doesn't generate preconditions and normal post conditions. JDoctor doesn't generate post conditions that are unrelated to return values. So in summary, we can see that the precision of our system is comparable with the state-of-the-art approaches, while the recall of our system is substantially higher. This table shows the effectiveness of our specifications in improving automatic test case generation. We chose JDoctor for comparison because of its diverse specification types. Our specifications lead to much lower false alarm than JDoctor's specifications do, and the total number of new oracles generated using our specifications is much higher than that of JDoctor's specifications. This table shows the effectiveness of our specifications in identifying leak paths. From the result, we can see that our specifications can identify much more leak paths than JDoctor's specifications. We can identify 50 more paths for 8 apps, while JDoctor can only identify 7 paths for 2 apps. Here are some related work. Thank all the previous researchers. In conclusion, we propose an automatic technique to derive formal program specifications from natural language comments. It works by assembling primitive tokens guided by specification syntax and properties of the target method. Our generated specifications can improve other software engineering tasks like automatic testing and static taint analysis. Thank you for listening.